In this lesson video, we're going to return to thinking about decisions under risk. And we're going to focus on a particular puzzle for the principle of maximizing expected utility. So we'll start by clarifying the nature of decisions under risk. And then we'll introduce a new distinction between normative and descriptive decision theory. And then we will cover the Allais paradox and use that to further illustrate this distinction between normative and descriptive decision theory. In the previous video, we covered rules for decisions under ignorance. In both decisions under risk and decisions under ignorance, the agent has to know all the possible outcomes in order to weigh them. The distinctive aspect of decisions under risk, though, is that the agent must know the probabilities of the outcomes, or at least be able to reasonably estimate them. So when we know the probabilities of the outcomes as well as their utilities for us, we can then calculate the expected utility of a choice based on the utilities and probabilities of the outcomes of that choice. And we determined that the rational decision to make under risk is the choice that maximizes expected utility. This will be important to remember coming up. So saying that a decision is rational is what's called a normative claim. It's a claim about what we should do. This is the foundation of the distinction between normative and descriptive decision theory. Normative decision theory offers prescriptions about what choice is rationally required in a decision problem. So it tells us we ought to make decisions in accordance to the guidelines of normative decision theory. When we've been discussing decisions under risk and decisions under ignorance, that's been a focus on normative decision theory. Expected value, expected utility, rules like maxi-max and dominance are all meant to guide what choice we should make in the face of a decision problem. As you might guess, though, sometimes people's decisions are rational and sometimes they're not, even when they have all the information that they need. The work that explains how people actually make decisions and predicts how people actually choose falls under the banner of descriptive decision theory. Descriptive decision theory tells us what people do choose, not what they should choose. The Allais paradox was initially proposed as a challenge to the normative principle, maximize expected utility. So for our purposes, we're going to focus on how it helps illustrate this distinction between normative and descriptive decision theory. Here's how the paradox is set up. We're asked to compare decisions between two gambles. As I read each decision, think about or even write down which gamble you would choose, and also think about or write down your reason for choosing it. So your first decision is between gambles 1A and 1B. In gamble 1A, you get $1 million for sure. And gamble 1B is a little complicated. You have a 1% chance of getting nothing, a 10% chance of $5 million, and an 89% chance of $1 million. Now you're presented with the second choice between gamble 2A and 2B. Gamble 2A has an 89% chance of nothing and an 11% chance of $1 million. So it's like a really good lottery. Gamble 2B has a 90% chance of nothing, but a 10% chance of $5 million. So slightly lower chance, bit more money. What would you choose in each case? In response to the first choice between 1A and 1B, most people choose the first gamble, 1A. They reason that they don't want to give up the 1 million for certain for only a small chance of getting the larger sum of money and that risk of getting nothing. And in the second choice, most people choose the second gamble. While the chance of getting $1 million is 1% higher in 2A than the chance of getting 5 million in 2B, most people think that's not really enough to override the chance of getting a much larger sum of money in that second gamble. So 2B looks more appealing. As I've hinted at so far, the Allais paradox highlights a gap between normative and descriptive decision theory. So in terms of the description of this pair of decisions, people tend to choose gamble 1A over gamble 1B, and gamble 2B over gamble 2A, as we've just talked about. Particularly notable about this pair of decisions is that people are really reticent to take risks in that first decision when they have a choice to get a good outcome for certain. However, this fact about how people do make decisions suggests that they are sometimes irrational. You might be surprised to know. Our normative theory for decisions under risk tells us to maximize expected utility. However, there's a problem with the Allais paradox. There's no utility function for money that would make it rational to make this pair of choices, 1A in the first decision and 2B in the second. It doesn't matter how you personally value money, choosing gamble 1A over 1B and 2B over 2A violates our rule of maximizing expected utility. That might not be obvious, so to show in detail that these choices are irrational and that they don't depend on your utility for money, first we're going to start by representing the utilities of each outcome abstractly. So this abstract representation tells us whatever your utility for $0 is, whatever your utility for $1 million is, whatever your utility for $5 million is, it will turn out that making this pair of choices is irrational, according to the maximization of expected utility. So whatever these three utilities are, they only have to stay the same across the two decisions, so that the utility of $0, $1 million, and $5 million are all fixed for you. We can then use these abstract utilities to calculate the expected utility of each of these gambles. So the expected utility of 1A is just the utility of $1 million because you get $1 million for certain. The expected utility of 1B is 1% chance of getting the utility of $0, 89% chance of getting the utility of $1 million, plus the 10% chance of getting a utility of $5 million. This is exactly what we should expect from our expected utility formula. And then in the expected utility of 2A, we have an 89% chance of getting the utility of $0, an 11% chance of the utility of $1 million. And finally, we add for the expected utility of 2B, the 90% chance of getting $0 to the 10% chance of $5 million. What we're going to do is use these four expected utility formulas to show that as long as the agent is consistent with their utility for money across gambles, there's no way that making choice A in the first decision and choice B in the second decision can be rational. To see that it's irrational to pick 1A over 1B and 2B over 2A, we need a way of comparing the two choices, the two decisions. We can show that the difference between the expected utilities of the gambles is the same for both decisions. So to get the difference in utility between the choices in each case, we're going to take the expected utilities we just determined on the previous slide. And for each decision, we're going to subtract the expected utility of the B choice from the expected utility of the A choice. So the expected utility of 1A minus the expected utility of 1B, we subtract the 1% chance of $0, the 89% chance of the utility of $1 million, and the 10% chance of the utility of $5 million from our utility for $1 million for sure. And then in the second case, the expected utility of 2A minus 2B, we have the expected utility of 2A, which is 0.89 times the utility of nothing, plus 0.11 times the utility of $1 million. And then we subtract the two terms of the expected utility of 2B, 0.9 times the utility of 0 minus 0.10 times the utility of 5 million. In the first one, we get to subtract the two that have the utility of $1 million. And so that gets us down to that formula in green. And then in the second, we get to subtract out the utility of $0. And again, that gives us the formula in green. What turns out to be the case is that the difference in utility between the gambles is exactly the same for both decisions. So if you look at those green formulas, they're exactly the same. Since the difference between the gambles is the same, to be consistent, you have to either prefer the first gamble in both or prefer the second gamble in both. So while people do choose 1A over 1B and 2B over 2A, those preferences are irrational. As we've just shown, they violate the principle that tells us to maximize expected utility. You can't maximize your utility in both decisions by making the A choice in one and the B choice in the other. If you're still finding it hard to see why you have to consistently make the A choice or the B choice in both, here's a way we can reframe the Allais paradox. We can set up the two choices so that they have the same outcomes, but they're represented in a way that helps us better see the similarities between the two A choices and the two B choices. So pay attention to what's similar between gamble 1A and 2A and 1B and 2B. So the following decision matrix offers our alternative way of representing these four gambles. The original Allais paradox was stated in terms of percentage chances, kind of abstract numbers. Well, now we're going to represent those chances concretely. So the chances don't change, but we're going to represent them in terms of proportions of 100 tickets. So basically a 1% chance is one ticket out of a set of 100. The benefit of setting this problem up in terms of tickets is that it allows us to represent all four gambles in a single decision matrix where we have three states. There's a ticket 1 state, there's the state where you draw a ticket between 2 and 11, and a state where you draw a ticket between 12 and 100. Why are they laid out this way? We can see why if we focus on gamble 1B. That's the one that gives us our three states, the three groupings of tickets. So if you draw ticket number 1 in gamble 1B, that gets you $0, right? There's a 1% chance of getting $0 in that gamble. If one of the 10 tickets 2 to 11 are drawn, you get $5 million. And if one of the 89 tickets 12 to 100 are drawn, you get $1 million. So again, those proportions are the same as the original choice. So this way of framing the problem is equivalent. Now for gamble 1A, you get $1 million for certain. And if we look at each of these states, doesn't matter which ticket group you're drawing from, you get $1 million no matter what. So this still accurately represents that choice. Now let's look at gamble 2A. There you have an 11% chance of winning $1 million. So ticket 1 will land you with $1 million, and tickets 2 to 11 will land you with $1 million, but the rest give you nothing. And finally, in Gamble 2B, the only tickets that give you a chance of winning are the 10, 2 to 11. Otherwise, you get nothing. Notice in 1A and 1B, 89% of the time, there's no difference between these gambles. If you look at tickets 12 to 100, the outcome of those two gambles is the same. And again, look at the difference in 2A and 2B for tickets 12 to 100. Ah, there isn't one. Doesn't matter if you choose 2A or 2B. If you're drawing from tickets 12 to 100, you get nothing no matter what you chose. So again, in decision 1, no matter what you chose, if a ticket from 12 to 100 is drawn, the outcome is $1 million. And in decision 2, no matter what gamble you chose, if a ticket from 12 to 100 is drawn, the outcome is the same. You get $0. Framing the decision this way, then, suggests that what you should focus on is what makes the A choice different from the B choice. So we're essentially going to ignore that third column because it doesn't help us differentiate our two choices in each of these decisions. And instead we're going to focus on just the first two columns. In the first two columns, notice that gamble 1A is the same as gamble 2A. In those first two columns for gamble 1A and 2A, they both give you that 11% chance at $1 million. And in gamble 1B and 2B, you have a 1% chance of nothing and a 10% chance of $5 million if you look at just the first two columns. So by reframing this decision, it's easier to see the parallels between the A options and the B options. And then this makes it clear that if you prefer the B option in choice 2, you also ought to prefer the B option in choice 1. Since in the states that make a difference, the B options and the A options are the same. What was the point of this reframing? It merely helps us see why it is that the expected utility of either the A option will be higher in both cases or the B option will be higher in both cases. So you must either pick the A option in both or the B option in both. The Allais paradox was initially presented as a potential challenge to the principle of maximizing expected utility. But in defense of expected utility, we've suggested that the paradox describes irrationality in people's actual choices, but leaves the normative guidance of expected utility intact. Because if we reframe the decision, we can see why it's rational to follow the guidelines of expected utility. However, as we'll see in the next video, expected utility does face some other issues, particularly from the problem of infinite utilities.